Okay, Organic Chemistry 2330. Here's our continuation on Chapter 10. This is 10.2, the basicity and reactions of amines. Okay, let's go on to look at the idea that all amines are weak bases, and therefore when we dissolve these amines in aqueous solutions, that solution becomes basic. Okay, so in the case of these amines, the amine will act as a base and the water acts as the acid, okay? So this is acting as the base and this is acting as the acid, which makes this the conjugate acid and the hydroxide is the conjugate base. And so if we look at our equilibrium constant here, we have our conjugate acid and our conjugate base is over our base and our acid here, okay? So from this equilibrium constant, we get an idea that they will always make these basic solutions when we dissolve them in water, okay? That being said, it's common to discuss these basicity of amines based on the ionization constant of the conjugate acid, right? So we can compare them on the same scale. We typically have all of the things we're looking at so far have been on the pKa scale, as far as very strong acids being less than 0, our strong organic acids like acetic being around 5, and then things running down to our alkynes and our alkanes as being on the pKa scale. So let's compare these on the pKa scale to get an idea about that. So if we look at our conjugate acid and think about its strength right here, we start with our protonated amine here, and it's interacting with water as our base. And so this becomes our conjugate acid and conjugate base, and this is our conjugate acid. So when we look at the concentration of this is our acid in the solution right here. This is our conjugate base in our solution here. And we find that our pKa value is around 10.6. Turns out we can convert our pKa value to our pKb value because the pKa plus the pKb will equal to 14, okay? So that's an interesting constant, especially in water-based systems. Okay, so that means that if our pKa is at 10.6 for our conjugate acid, that means our pKb for our free amine is going to be that minus 14, so it's going to be 3.36, okay? So our pKb is 3.36, so let's keep that in mind right here. Okay, so let's compare some amines with their pKa values and their pKb values, okay? So when we look at this, we can say, okay, let's compare our strength of our acid on this side of our equation with our strength of our acid on this side of the equation. So if we look at our pKa value for this methylamine that's been protonated, we can say its pKa value is 10.64. We know that the pKa value for acetic acid is around 5. It's actually 4.76. And what that means is, remember that the lower the number, the stronger the acid. So that this number is lower than this number, which means it's the stronger acid. If it's the stronger acid, everything when we do an acid-base reaction wants to go to the weaker side of the equation. Therefore, methylamine will react with acetic acid to push the equilibrium to the right side of the equation to get to the weaker acid and the weaker base. Okay, so what does this look like on our regular pKa scale? Okay, so we're going to first look at aliphatic amines and then we're going to look at aromatic amines. I'm going to blow this scale up here so that we can see this, okay? So if we look at the pKa of the conjugate acid of ammonia, we see the pKa of the conjugate acid of ammonia, the protonated form, is 9.46, which means its pKa is 14 minus the 9.4, which is that 4.76, okay? So just like in the pKa scale, the lower the number, the stronger the acid, The pKb scale is the same. The lower number, the stronger the base. Okay, so let's look at the whole series here. So if we have primary amines, we have them all in the 10 range, and the secondary amines are all in the 9 to 10 range here, which means that the base strength of all of our primary amines is right around the 4 to 4 range here. Okay, so if we look at the pK of these acids right here, they're all about the same. Okay. Now let's compare that to our aromatic amines here. Okay, first off, if we look at our pKa's for our aromatic acids, they are all lower than our pKa's for our aliphatic acids. Okay, which means they are stronger acids. Okay, if these are stronger acids because their numbers are lower, and then we do the conversion with our 14, we actually end up with higher numbers for our pKb's. Okay, because these are stronger acids, these are now weaker bases than the aliphatic ones. Okay, it's weaker bases. So aliphatic amines are stronger bases than aromatic amines. Okay, and we're using that conjugate acid pKa scale to compare and contrast with what we already know about our acidity scale. Okay, so even if we have a structure that looks very similar for the amine content and the number of carbons we have, the aliphatic amine will always have the stronger base strength right here because the pKa of our conjugate acid is higher. Okay, so our aromatics are always weaker bases than our aliphatics. Okay. The reason our aromatic amines are always weaker bases than our aliphatics is the fact that we can take the lone pair that's acting as the base and it can move onto the ring and be delocalized around the set of resonance structures here such that it spends less time up on the nitrogen. Therefore, there's less time of these lone pair to be just set on the nitrogen, and therefore it decreases their base strength. If we look at the cyclohexane derivative here, there's nowhere for those electrons to go. They stay on the nitrogen the whole time, and therefore they are more likely to accept a proton. Therefore, they are a stronger base. Okay, so once we have the idea that the delocalization of those electrons onto the ring decreases the base strength, we can change the base strength by adding different groups to the benzene ring. So if we have electron withdrawing groups such that it even spends less time here, we can actually decrease the base strength even more by adding electron withdrawing groups. We can increase the base strength slightly by adding donating groups, but by adding these withdrawing groups, we can decrease the base strength even more. Okay, so another thing we need to know about amines is that almost always, if you have an amine and you react it with a strong acid, it makes them water soluble.
Norepinephrine.
This norepinephrine here is very poorly soluble in water. It's a neurotransmitter and hormone used in the human body. And when we react it with HCl, it makes a very highly water-soluble hydrochloride salt. In fact, if you look at a lot of the prescription drugs we have and pharmaceuticals we have, you'll see a lot of them have some kind of compound plus hydrochloride or hydrogen sulfate or something like that, meaning they were made into the salt to make them more water soluble. This is done extensively with amines because almost all of them are completely water soluble as the salt. Okay. So how do we synthesize primary amines? The most common way to synthesize primary amines on an aromatic ring is to actually nitrate the ring and then reduce down that nitro group to an amine group, okay? And this makes a single primary amine because you started with a nitro group and then we're adding hydrogens where the nitros were and regaining our lone pair. Okay. Now, for aliphatic reactions, what we have, we can also use our nitrogen here as a nucleophile, which means that if we have an alkyl halide, we can convert an amine that is of primary or less to a primary, secondary, or tertiary thing by reacting it as a nucleophile. So we can take the lone pair of the nucleophile, we'll react on an alkyl halide to displace the chlorine to create this um, salt right here, this ammonium salt with here. The next thing that happens is we transfer the proton off of the ammonium salt to give us our free amine back, plus some other uh, salt of material. Now, once we formed that reaction where we've put one of these R groups on, we still have a lone pair. And if we put a second R group on, we still have a lone pair. The lone pair is the part that's acting as the nucleophile. So what can happen is once we reform this free amine, it can react again and again and again. So there's no stopping it until it reacts to substitute all of those hydrogens with the alkyl groups, which means it's very hard to make a stop at just a secondary or a primary amine if you're doing it using nitrogen as a nucleophile. Okay, so we would typically, if you want to get to the tri-substituted here, or even the quaternary ammonium salt, that would be a useful reaction using it as a nucleophile. But if you're trying to stop at a primary or a secondary, it's not going to stop. You're going to get a mixture of the different components because it will always act as a nucleophile as long as it has that lone pair. And that is the two reactions we're going to do with amines.